Hello everyone, welcome back to my organic chemistry mini lecture again. Today our topic will be the malonic ester synthesis and acetoacetic ester synthesis. Before we talk about that two syntheses, we will first talk about decarboxylation. The decarboxylation is the reaction that decomposition of the reactant and release carbon dioxide, and so that's called a decarboxylation. The first example of that reaction is the malonic acid. You can see the structure shown here. It's two acid here, and if you redraw this one of the carboxyl group and basically rotate this single bond here, and then you can rotate this hydroxyl group to here and rotate the carbonyl group to here. So, and then when you heat up this compound, this pi electron of the other carboxyl group, the carbonyl pi electron can deprotonate this proton, and then the sigma electron here between the hydrogen and oxygen can push back to form a pi bond here. At the same time, break this carbon-carbon bond and then push that electron to here to form a new pi bond. So you will form this intermediate, and you can see this is actually like enol. Of course, you have another hydroxyl group, but this moiety is more like enol, and the byproduct is carbon dioxide. See, carbon dioxide, 1 carbon, 2 oxygen. And then this can undergo tautomerization. So first is the protonation, and the oxygen will push the lone pair back to form the pi bond and push this pi bond between these two carbon to take the proton, and then you have this protonated intermediate. The base can deprotonate this proton and then neutralize this positive charge of the oxygen, and so the final product is the neutral carboxylic acid. So this process is called a decarboxylation, and decarboxylation of malonic acid will lose one carboxyl group and have another carboxyl group left. Another compound can also undergo decarboxylation. That's beta keto acid. So the difference with this malonic acid is this is actually ketone here, not carboxylic acid. So just one acid, but they are similar because they all have the beta oxyl group here. So this group can help the decarboxylation. So again, we can redraw this carboxyl group here to rotate 180 degrees. Then you can have the same orientation as this first reaction, and then same reactivity. You can see the carbonyl pi electron can deprotonate this proton, push the sigma electron back to form the pi bond here, and break this carbon-carbon single bond and push the electron back to form this pi bond here. So you can see after heating, after high temperature, and then you will have this enol and carbon dioxide. Enol will undergo tautomerization, same thing as that first example. First is the electron from the oxygen push back to form the pi bond and push this pi electron to take the proton. So that protonation gives you the protonated ketone intermediate. And then the base can deprotonate the proton and neutralize this positive charge, and you can get this neutral ketone as a final product. If you have the beta keto acid, after decarboxylation, you will form a ketone. So you can see decarboxylation always lose one carboxyl group. Okay, keep that in mind. We will talk about first the malonic ester synthesis. The malonic ester synthesis is utilize the enolate generate by deprotonation of the alpha proton and react with the alkyl halide And basically SN2 reaction, that second step basically is alkylation. And third step is the workup with the acid that have several reactions happen in this step. First is the hydrolysis of the ester to carboxylic acid, then decarboxylation happened. Final product will be acid. And this acid will have more carbons. Those carbons is from the second step, from the alkylation. The mechanism is a little bit long. We'll talk about step by step. Okay, first is the alpha proton of this malonic ester be deprotonated by the base. The base here is methoxide. So that should be the same as this ester's R group, alkoxy group. And then deprotonation happen here. So the base take the proton and push the sigma electron back to form the pi bond and push that pi electron to oxygen. And that deprotonation form this enolate moiety. This part structure is enolate. It's a nucleophilic. And then second step, we have the example here is ethyl bromide. This nucleophile will react with this electrophile. So the electrons of oxygen will push back to form the pi bond, and this pi electron will be pushed to tag this carbon with the leaving group, and then kick off the bromide. So that is basically a SN2 reaction, and also its alkylation. Then this carbon will form a new carbon-carbon bond with this ethyl group. And then this neutral intermediate can react with the acid. Basically now we are going to do the third step, and that's hydrolysis of the ester to carboxylic acid. We have two esters, so I will do one by one. And first protonation, and then water. After protonation, this is activated, and then water will be a nucleophile attack this activated carbon, and then push the pi electron to the oxygen. After this nucleophilic addition, you can form this tetrahedral intermediate. This will have a proton transfer. The oxygen will take the proton here, and then neutralize the positive charge by this sigma electron. And then after this proton transfer, you will convert this group, the methoxy group, to methanol, much better leaving group. Now it will be kicked off by one of this hydroxyl group. The lone pair of the oxygen can push back to form the pi bond and kick off this methanol as a leaving group. And then that elimination give you this protonated carboxylic acid here, actually. And then next step, we need to hydrolyze the other ester. So we have another proton transfer. This oxygen take the proton, push the electron back to the oxygen here to form activated ester. This carbonyl group will be activated. So water, again, as a nucleophile, can attack this carbon and break the pi bond. Then, after this nucleophilic addition, you can see it's very similar, basically repeating the first step here. And then we have another tetrahedral intermediate. And after another proton transfer, this oxygen take this proton and then push the sigma electron back to the oxygen. And then this methoxy group will be converted to methanol as a better leaving group. Next step is just the elimination. So the electron from the oxygen push back and then form the pi bond, at the same time kick off this leaving group to form the protonated acid again here. So we will need to use a base, depronate this proton, and push the sigma electron back to the oxygen, and to neutralize this positive charge. And then we have this neutral is a diacid. And then next step, just decarboxylation. We already showed the mechanism in first slide, so I'm not going to show that steps again. But decarboxylation will remove one of this carboxyl group. Since these two are symmetrical, so it doesn't matter which one you remove. So just get rid of one of carboxyl group. Then this example, I get rid of one with this carboxyl group, and then we have the final product is this acid. It's a butanoic acid. So yeah, it's a little bit different join. So you just rotate this single bond, you will have exactly the same structure. This is the very typical malonic ester synthesis, the arrow pushing mechanism. Okay, next we will talk about another possible malonic ester synthesis with double alkylation, because when we do the first alkylation, you still have another alpha proton. So potentially we actually can do another alkylation, use a different alkyl halide. You can use the same one, but you can use a different one. So you can make a different product. Okay, last step always be the same. Work up with acid and heat up. Let's look at the mechanism. So you can see the product here is a substituted carboxylic acid. So mechanism, first step is the same, deprotonation of the alpha proton by the base, and you make this enolate. This enolate will react with the alkyl bromide. The first step is the ethyl bromide, and then this electron of oxygen push back and push this pi electron to attack this carbon, kick off the leaving group, and you can form this neutral intermediate. This is the alkylation here. So you have ethyl group here connected with this carbon. Now we actually have another alpha proton, and this alpha proton can be deprotonated again by the same base and form the, yeah, I put this first, sorry. So, and you form this enolate. And then this enolate will react with the other alkyl halide. This example is a propyl 1 propyl bromide. And then the nucleophile here is this enolate, and then the oxygen electrons push back to form the pi bond and push the pi electron to attack this carbon and then kick off the leaving group. That's another SN2 reaction, and that's also alkylation. And then you will have another alkyl group connected to this same carbon here. So that's double alkylation complete. And then after that, we just go to the last step, hydrolysis. Under acidic condition, these two ester will be converted to carboxylic acid. This is diacid. And then under high temperature, so this one of the carboxyl group will be decarboxylated. And so after the decarboxylation, it will form this acid. The other carboxyl group will be removed. So, and this is the substituted. So this is the 2-ethyl pentanoic acid. Okay, that's the mechanism. So I didn't show the detailed step of the hydrolysis and the decarboxylation because we already talked about it in the previous slides. This is the malonic ester synthesis. And the other synthesis is the acetoacetic ester synthesis. And it's a very, very similar synthesis, just use a different starting material. So not the malonic ester, but as acetoacetic ester synthesis. Condition is the same. Product is ketone here, not carboxylic acid like the malonic ester synthesis. And you may notice the mechanisms are very similar. The first step is the alpha proton here be deprotonated by the base. So, and deprotonation and push the sigma electron to here to form the pi bond and break the pi bond to the oxygen. And then after that step, you can form this enolate. It's a very similar intermediate. React with this ethyl bromide. And this leaving group will be kicked off by this pi electron. The arrow pushing start from the electrons of oxygen here. So that is another SN2 reaction. And also alkylation happened. So ethyl group here connect to this carbon. And it's the same as the previous slides. We can do another alkylation. You can choose another different alkyl halide, and you can do another alkylation here. But in this example, I didn't show the second alkylation. It's up to you. Okay. So next step is just the hydrolysis of this ester. We only have one ester here, so only this ester will be hydrolyzed to carboxylic acid. Again, I will not show the mechanism again because I already did the in previous slides. Now, after you get this neutral intermediate, basically that's a substituted beta keto acid, and high temperature will form this a decarboxylation reaction and just remove this carboxyl group. So our final product is the ketone. This is the methyl propyl ketone. So basically remove this group, so what's left is the ketone. That's the product. Okay, so like I said, you can do double alkylation. So I will show the example of the double alkylation and use a special alkyl halide is this dibromide here. It's 1,4-butane, 1,4-dibromobutane, sorry. So use the same condition, the base, and use this alkyl halide and this last step, work up in acid. You can actually make a ring system here. So that's a cyclization. And now, first step, it's again just the deprotonation of the alpha proton by the methoxide, the base, deprotonation, and form this enolate. This enolate can react with this dibromide. One of the bromide first will be kicked off, so SN2 reaction. The electron push back from oxygen and push the pi electron to attack one of the carbon with the leaving group, and then kick off the bromide. And then we first form the carbon-carbon bond between the carbon and this carbon. This is the new bond formed. And we still have the alpha proton that can be deprotonated again by the base and form this enolate. So you may notice I draw the enolate this way. This is actually the resonance of the normal enolate form I drew. So here I just draw this way. It's the same. And then this enolate can attack this carbon with the leaving group. So that is another SN2 reaction, kick off the leaving group. And then we can form this 5-member ring. Okay, it's a cyclopentane ring here. And then next step, we can just hydrolyze this ester to carboxylic acid. And then decarboxylation happened to remove this carboxyl group. And then this is the final product, the ketone. Okay, so that's all I want to talk about these two syntheses. And if you have any question, please let me know. Good luck.